Good afternoon. I am Ciprian, and today I will discuss my submission for the self-balancing robot, as well as its features and real-world limitations. The purpose of this robot is to use a PID controller that has been turned accordingly in order to have the robot stay balanced perpendicular to the floor. This is required because the robot is only using two wheels. Furthermore, the robot should withstand light external disturbances and must be able to be controlled from the labial interface by a user. There should also be a claw mechanism that is able to pick up a ball over podium, and once picked, have a green LED blinking, and when the ball has been placed, there should be a red LED that's blinking. There should also be features that are focused on autonomy, and they should happen without any kind of user interaction. So the actions that will be demonstrated today are self-balancing in a default state, which can withstand external disturbances, manual movement of the robot and claw from the user in order to move towards the ball and pick it up, automatic claw control for picking up the ball without user input, and finally, manual control to reach a container where the ball will be placed. There will also be an experimental demonstration of an autonomous movement done by the robot based on external factors and sensor data at the end. So my robot has been properly simulated into the NX software with right physics, collision bodies, rigid bodies, sensor data, transmission between the lab view and the NX interface. And if I press start on the simulation, you can see that the robot at the moment is balancing based on the PID gains that have been tested multiple times. And after many rigorous attempts, I found that Kp equal to 15 and Ki equal to 0.008 are the best values. Now, as I said earlier, the robot has to stay perfectly balanced and also withstand an external disturbance. As you can see, I'm moving the robot and the robot is still perfectly fine. And there should also be a manual control from the user. In my case, the user not only can control the robot if it goes backwards, forwards, left or right, but it can also control the turning speed and movement speed. So let's try to go and pick up the ball and discuss about the claw and how it works. The ball has been placed on a podium that is a 20mm ball in diameter with a rubber material applied to it and collision body. And if I reduce the turning speed, I can have it a bit better. Now the robot, if it's parallel to the podium, it helps, but it does not have to be. The podium can be made as a cylinder, and then this limitation would be completely removed. Now that I'm close and parallel to the wheel, to the wall, I want to show you that the claws mechanism, which completely retracts inside the robot's body, can be moved manually by the user using these sliders from 0 to 100 degrees, both of them. So a user can pick any type of object by just simply changing the angle of the claw. Now, there is also an automatic claw system that I have developed. While if the user flips the switch on, the claws return to 0 and they retract inside the body. And now, based on the sensor value and the claw grip that has to be inputted by the user beforehand, the ball will be picked up automatically. What this means is that when I pick up the ball manually, I can see what kind of sensor value I have by looking at this. From the sensor itself, this is an infrared sensor, the distance infrared sharp sensor, to the ball, and then also what's the angle of the claw in order to pick it up. This is very useful in a factory environment. Once we have picked up manually once, we can know exactly what the values that we are required, and then just input those values, and the robot would do it automatically. So let's change the view from up top. The automatic claw is engaged, and now if I just go forward, once it reaches the ball, it picks it up and then it goes backwards, and the green LED starts blinking. Now, let's try to move the robot towards the container, which is there. Let's increase the turning speed. Let's move to the left. Let's reduce the speed by a bit. Let's go forward. As you can see, the robot stays perfectly balanced even with the clothes fully open and with a ball, a robot ball that doesn't have that much weight, but it is still extra weight nonetheless. Let's make it so it's from the top again. And let's zoom in. Let's try to go towards the box. And once I am on top of the box, as you can see here, let's go a bit to the left. Now I'm on top of the box. I can just release the claw. So let's go forward a bit. Can release the claw. The red LED starts blinking. The green LED stops blinking. Let's increase the speed and go backwards a bit. And the ball has been placed inside the box itself. Now, the main features of this robot is the fact that it is very compact. It has a very small design. We're talking about around 15 centimeters by 20 centimeters. The MyRio device can be completely removed. It works on a slide based on a sliding mechanism, so that makes the robot even smaller if it is required to be moved anywhere. And the claws completely retract inside the body. Not only this, but because the claw is based on two different servos that are SG90s, these servos are 10 centimeters away from them, so from the body, they're able to pick up 2.5 kilograms. Now, of course, the robot itself will not be able to pick up that much since the weight of the robot is nowhere near 2.5 kilograms, but that is a very good specification to have for the robot. So the weight of the item that is picked up is not a problem. Furthermore, because of the claw that can be manually moved and then manually programmed so that the action happens automatically, this robot will work very well in a factory-like environment. Furthermore, the user interface has been highly detailed so that when there is research done and testing done on the robot, so let's say in a real life scenario, is this simulation has to be applied to a real life robot, the user can see all the outputs and all the information in order to react accordingly and change the required variables. I also added the motor RPM, which is connected to the PID highest output and lowest output, so that if in real life the motors that I use are not of 197 RPM, like the ones that I used in the simulation, the user can change this output without actually having to change the constant inside of the block diagram in LabVIEW. A small issue that this robot has is that inside of a factory environment, it does not work autonomously. So it still requires manual movement from the user, although the claw happens automatically. Now, in the next section, I'll show you my experimental autonomous program and the idea behind it. Now, in the second section of this video, I went ahead and changed the simulation environment and the LabVIEW code to something that is very similar, but this time there is no manual input to the robot, so the robot cannot be controlled. What happens though in this environment is that the robot now has an infrared sensor, a sharp infrared sensor, on the opposite of the one that picks up the ball, and this sensor can see up to 1.5 meters. The way this has been programmed and the idea behind it is that the robot can rotate in place and act as a radar, and when the infrared light beam hits an object, it detects that object and it goes towards it. So as a demonstration, if I click play, you can see that the robot will turn in place into its default state and it will stay balanced. And once it detects the podium, it will stop and then it will go towards the podium. As you can see, it's going towards it. Now, when it is very close to the podium, in my case, 300 millimeters from it, I will just stop. So you can see the robot stopped. Now, This is very useful because if I change the podium in any place, it will always go towards it and will always detect it. So this feature would be very useful in an environment where we do not know where the podium is and how we can reach it. But if the robot can reach it, it will do it automatically without any kind of user input. Now, this is where the highly experimental demonstration of autonomy stops. But the next points would be to make the robot rotate on itself so that the automatic clock can engage, pick up the ball, start rotating again with the rudder function, find the box for the ball, the container, and then go towards it and then release the ball once it reaches close to it. So that has not been yet fully developed, but as an idea, that works perfectly. Another way that can be done is we can have the robot use the radar function to find the podium, and then a line following track towards the box container in order to have the robot go towards the container itself. With all this said, this has been my full demonstration of all the progress that have been made in NX and LabVIEW in order to have a self-balancing robot that follows the brief accordingly and also has extra features that have not been requested in terms of autonomy. Thank you for watching